In March 1995, a state engineer drove into Izard County, Arkansas, with a laptop and a demolition order. His structural analysis software, the most advanced available, had calculated that a wooden-covered bridge, built in 1961 by a local carpenter, could not survive a Category 3 flood. The math was clear. The bridge had to go. 6 weeks later, a Category 4 flood hit, 53% beyond what any model predicted. 3 bridges built with modern concrete and modern engineering gone within 24 hours. The wooden bridge, still standing, carrying ambulances, carrying school buses, the only crossing left in 7 miles. The engineer came back. And this time, he came to listen. The morning Arthur Finch drove into Izard County for the first time, he almost missed the bridge entirely. He had been watching the road, following the directions his secretary had written on a yellow notepad left at the grain elevator. 2 miles on the blacktop, then right onto County Road 14, and when he finally looked up, there it was. A covered wooden bridge sitting over Piney Fork Creek like something that had grown there naturally, the way a fallen log crosses a stream in the woods. It was painted barn red, though the paint had faded to something closer to the color of old brick. The roof was cedar shake, patched in 3 places with newer shingles that stood out against the weathered originals like fresh stitches on old skin. A hand-lettered sign above the entrance read, "Whitfield Bridge built 1961, 1 lane, proceed with caution." Arthur Finch pulled his state-issued Ford Bronco to the side of the road and got out. He stood for a moment, looking at the bridge with the expression of a man who has already made up his mind and is simply confirming what he already knows. He was 48 years old. He had a master's degree in civil engineering from the University of Arkansas, a decade of experience with the Arkansas Department of Transportation, and a laptop computer running SAP 2000, the most advanced structural analysis software available to state highway engineers in 1995. He had used that software to evaluate 43 bridges across 7 counties in the past 3 years. He had recommended the demolition of 11 of them. He pulled a clipboard from the passenger seat and wrote the date, the 14th of March 1995, at the top of his inspection form. The Whitfield Bridge, according to his records, was 34 years old. It had been built in 1961 by a local carpenter named Clarence Whitfield, using what the engineering file described as a town lattice truss configuration. A bridge design patented in 1820 by architect Ithiel Town, using crisscrossed diagonal planks pinned together with wooden tree nails to form a continuous lattice of overlapping triangles. The file noted that Clarence Whitfield had built the bridge using white oak harvested from his own land, hand-split tree nails, and a set of hand-drawn plans that his grandfather had copied from a Civil War-era builder somewhere in Tennessee. The file also noted that the bridge had never been formally load-rated. It had simply existed, year after year, carrying farm trucks and school buses and the occasional grain wagon, because it was the only crossing on Piney Fork Creek for 7 miles in either direction. Arthur Finch walked to the entrance of the bridge and peered inside. The interior was dim and cool, smelling of old wood and creek water. Shafts of light came through gaps in the siding where boards had shrunk over the decades. The lattice walls rose on both sides, hundreds of diagonal planks crossing each other at angles, pinned at every intersection, with wooden pegs the diameter of a man's thumb, creating a geometric pattern that seemed almost impossibly intricate for something built by hand in a rural county in 1961. He knocked on one of the diagonal planks. It sounded solid. He made a note on his clipboard. Appears structurally sound surface inspection only. Full SAP 2000 analysis required. Then he drove across the bridge slowly, feeling the slight flex of the deck planks under his tires, and continued down County Road 14 to find Clarence Whitfield. Clarence Whitfield was 78 years old and did not look like a man who built bridges. He was short and lean, with hands that were too large for his body carpenter's hands, with knuckles that had been broken and reknit so many times They sat at angles that no longer aligned with the standard geometry of a human fist. He was sitting on the porch of his farmhouse when Arthur Finch pulled into the yard, shelling dried corn into a bucket with a mechanical motion that suggested he could do it in his sleep. He watched Arthur Finch get out of the Bronco, collect his clipboard and laptop case, and walk toward the porch with the careful stride of a man navigating unfamiliar territory. "Mr. Whitfield?" Arthur said. "That's me. Arthur Finch, Arkansas Department of Transportation. I called last week. I remember." Clarence set the corn aside and folded his hands in his lap. "You want to tear down my bridge?" Arthur Finch sat down in the offered chair and opened his laptop. The screen glowed pale blue in the morning shade. He turned it so Clarence could see. "I haven't made any final determination yet," Arthur said. "That's why I'm here. The department is conducting a systematic review of all non-standard bridge structures in the region. Your bridge was built without state permits, using non-engineered plans, and has never been formally evaluated for load capacity. Before we can allow it to remain in service, we need to verify that it meets current standards." "What standards?" Arthur pulled a document from his clipboard, dense with tables and specifications. "AASHTO HS 20 loading. That's the minimum threshold for county road bridges, the equivalent of an 80,000-pound semi-trailer. Your bridge is a single lane, 42 feet long, built of white oak in 1961. Based on the dimensions in our file, my preliminary SAP 2000 analysis suggests a maximum safe load of approximately 22 to 25,000 pounds. Clarence looked at the laptop screen. The SAP 2000 interface showed a three-dimensional wireframe model of the bridge, or rather, a simplified representation of it. The lattice structure had been modeled as a series of individual beam elements, each assigned material properties based on standard published values for white oak. "That's not what my bridge looks like," Clarence said. "It's a structural model. We use simplified representations to calculate stress distributions. That's not how the bridge works," Clarence said. He went back to shelling corn. Arthur Finch looked at him for a moment, then looked back at his laptop. He had encountered resistance before from farmers, from county commissioners, from local historians who wanted to preserve every old structure regardless of safety. He was not unsympathetic, but he had a job to do, and the job was governed by numbers. "Mr. Whitfield," he said, "I understand this bridge has personal significance to you. You built it yourself. But my analysis indicates that it cannot safely support current traffic loads, and more critically, it cannot withstand a Category 3 flood event on Piney Fork Creek. The White River Basin is showing increased flood risk due to upstream development. We have had 2 significant flood events in this county in the past decade. The department's position is that the risk to public safety outweighs the historical value of the structure." Clarence finished emptying the corn into the bucket. He set the bucket aside and looked at Arthur Finch directly for the first time. "How old are you, son?" 48. "Have you ever built a bridge?" "I've engineered the construction of 14 bridges in this state." "That's not what I asked." Clarence stood up, with a stiffness that suggested his knees had been disagreeing with him for some years. "Come with me." He led Arthur across the yard, past the barn, and down a path through the woods to the bank of Piney Fork Creek, about 100 yards upstream from the bridge. The creek was running high for March brown with silt, moving fast from recent rains. They stood on the bank and looked downstream at the bridge from the side. From this angle, the structure was transformed. The lattice walls, seen in section, revealed their geometry with perfect clarity. Hundreds of diagonal planks crossing each other at angles between 45 and 60 degrees, pinned at every intersection, creating a web of overlapping triangles that ran the full length of both sides of the bridge. The visual effect was almost organic, like the cross-section of a bone or the internal structure of a leaf. "My grandfather learned this from a man named Elias Carr," Clarence said. Carr had learned it from a builder who worked on covered bridges in Tennessee during the Civil War. The original design came from a man named Ithiel, an architect from Connecticut. He patented it in 1820. I know the history, Arthur said. Then you know why it works, Clarence said. The lattice distributes load across multiple members instead of concentrating it at primary load points. Yes, that's accounted for in my model. No, Clarence said quietly. It isn't. Arthur looked at him. Your model treats each plank as an independent structural element, Clarence said. But the planks aren't independent. Every intersection point, every place where two planks cross and are pinned together transfers force between them. When one plank is loaded, it shares that load with every plank it touches, and every plank it touches shares it further. The load doesn't travel in a straight line from the deck to the foundation. It travels through the lattice the way water travels through a web. It finds every possible path simultaneously. He picked up a stick from the ground and drew in the soft mud of the bank a grid of crossing lines. He pressed his finger at one intersection. Press here, he said. Where does the force go? Arthur pressed with his own finger. In all directions along the grid. Exactly. Now, in your computer model, how many load paths does the force take? Arthur said nothing for a moment. The SAP 2000 model had assigned each plank element fixed material properties and analyzed the structure under standard load combinations using classical beam theory. The connections had been modeled as pinned joints. It was the standard approach for timber bridge analysis. But it was not, he suddenly understood, an accurate description of what he was looking at. In a town lattice truss with hundreds of intersection points, each pinned with a wooden tree nail that had been compressed and swollen by decades of moisture cycling, the connections were not simple pins. They were semi-rigid nodes in a redundant network, a network so redundant that even if 30% of the members were removed, the remaining structure could redistribute the load. The SAP 2000 model had captured the geometry. It had not captured the physics. My grandfather told me, Clarence said, putting the stick down. Computers calculate according to today's formulas. White oak learns to endure over 200 years. Don't argue with something that has survived what you haven't yet seen. Arthur Finch stood on the bank for a long time, looking at the bridge. Then he drove back to Little Rock. The formal load rating report was completed on the 28th of March 1995. It ran to 47 pages, including appendices, and concluded with a single summary finding. The Whitfield-covered bridge on County Road 14 was not compliant with AASHTO HS20 loading requirements and could not be certified to withstand a Category 3 flood event. Recommendation: scheduled demolition. September, $1,995. Estimated replacement cost, $340,000. Arthur Finch signed the report. He stared at his signature for a moment before filing it. The report was distributed to the Izard County Road Department, the county judge's office, and the local newspaper, the Melbourne Mountain Wave, which ran a front-page story under the headline, "State Plans to Demolish Historic Whitfield Bridge." The story included a photograph of the bridge in winter light, looking handsome and solid, and a quote from County Judge Harold Bowles, "I have driven across that bridge for 40 years. It seems a shame." It also included a quote from Clarence Whitfield, "The bridge will outlast the report." The story was picked up by the Arkansas Democrat-Gazette. Readers sent letters. A historical preservation group in Fayetteville contacted the county judge. An engineering professor at the University of Arkansas named Dr. Margaret Sellers wrote a letter to the Department of Transportation arguing that the SAP 2000 analysis was methodologically inadequate for evaluating a redundant timber lattice structure. Arthur Finch read Dr. Sellers' letter 3 times. He agreed with approximately 60% of her arguments. He filed the letter in the case folder and continued with the demolition timeline. The demolition was scheduled for the 15th of September 1995. A contractor from Batesville had been engaged. The paperwork was complete. Then April arrived. The spring of 1995 had been wet throughout the White River Basin. February had brought record snowfall to the Ozark Plateau. March had been warm, too fast, melting the snowpack and saturating the soil before the ground could absorb the runoff. By the first week of April, the White River was running at 140% of its average April flow. The tributaries were at 160%. The National Weather Service issued a flood watch for Izard County on April 4th. On April 7th, a slow-moving, low-pressure system stalled over the Ozarks and began dropping 2 to 3 inches of rain per day on already saturated ground. The soil, unable to absorb any more moisture, shed the rain immediately into the creek systems. Piney Fork Creek, normally 18 feet wide at the bridge crossing, began to rise at a rate of 8 inches per hour. By the morning of April 9th, Piney Fork Creek was running at 31 feet, 13 feet above flood stage. The Category 3 threshold, defined in Arthur Finch's report as a flow rate of 12,000 cubic feet per second, had been exceeded. The actual flow was measured at 18,400 cubic feet per second, a Category 4 event, exceeding the design parameters of every flood model the Department of Transportation had used in its analysis. Category 4 was not supposed to happen. The standard hydrological models used by the Arkansas DOT in 1995 were based on historical flow data from 1927 to 1985. They did not account for the upstream development, the cleared farmland, the impervious road surfaces, the reduced riparian vegetation that had accelerated runoff rates throughout the White River Basin over the preceding 20 years. The models said Category 4 was a 1-in-200-year event. The creek said otherwise. The first bridge to fail was the concrete culvert crossing on County Road 8, 3 miles south of Melbourne. It was a poured concrete box culvert, installed in 1989, designed to handle Category 3 flows. The creek undermined the south approach embankment during the night of April 8th. By morning, the road was hanging in the air over a 6-foot gap where the embankment had been. A milk truck driver discovered the failure at 6:15 a.m., stopping 4 feet short of the edge. He sat in his truck for 20 minutes before his hands stopped shaking enough to use the radio. The second bridge to fail was the precast concrete girder span on State Route 58 at the North Fork of Piney Creek. This was a newer structure built in 1991, permitted, engineered, inspected annually. The design flood for this location was a Category 3 event with a peak flow of 9,500 cubic feet per second. The actual flow on April 9th reached 14,200 cubic feet per second. The bridge was struck by a debris raft, a mass of uprooted trees, fence posts, and farm equipment, which hit the upstream face of the center pier with an estimated impact force of 340,000 pounds. The pier held. The deck did not. 3 of the 5 precast girder spans were displaced laterally, leaving a 30-foot gap in the roadway. The third bridge to fail was the steel I-beam span on County Road 22, which crossed Piney Fork itself about 2 miles upstream from the Whitfield Bridge. Built in 1987, its approach embankments had been constructed of compacted clay fill standard practice. But clay fill, when saturated and subjected to sustained hydraulic pressure, does not behave like a structural material. It behaves like a slow liquid. By the evening of April 9th, the approach embankments had eroded to the point where the steel beam ends had lost their bearing. At 9:18 p.m., with no warning and no witnesses, the south approach dropped 14 inches. By morning, the span was impassable. 3 bridges, all built within the past decade. All engineered, permitted, and certified. All gone in less than 24 hours. Clarence Whitfield had been watching the creek since April 7th. He had a gauge, a stick he had driven into the creek bank in 1961, graduated in 6-inch increments, painted white so he could read it from the porch with binoculars. He had written the readings in a notebook every morning and evening for 34 years. He knew this creek's behavior the way a physician knows a patient, not just the average, but the variations, the anomalies, the way it behaved differently when the rain came from the northwest versus the south, the way it crested faster in April than in March. By the morning of April 9th, his gauge read 31 feet. He had never seen it above 28. He put on his rubber boots and walked to the bridge. The water was 8 feet below the deck, not touching the structure yet, but close. The current was enormous, carrying a continuous cargo of debris, branches, entire small trees, sections of fencing, a propane tank, the remains of what appeared to be a chicken coop. The roar of the water could be heard from the farmhouse, half a mile away. Clarence walked across the bridge slowly, the way he always did, not from fear, but from habit. He had walked this bridge thousands of times since 1961. He knew every plank, every tree nail, every place where a board had been replaced. He put his hand on the lattice wall as he walked, feeling the slight vibration of the wood under the hydraulic pressure of the rising water. The bridge was alive. That was the only way he could describe it. A concrete bridge under load was rigid. It either carried the load or it didn't, and if it didn't, it broke. A town lattice truss under load was dynamic. The hundreds of intersection points allowed the structure to flex microscopically, distributing stress, relieving pressure concentrations, adapting. The white oak, dense and hard and seasoned by 34 Arkansas winters, absorbed energy without fracturing. The tree nails, swollen tight by decades of moisture, transferred shear forces between members with a consistency that no bolt or nail could match. The bridge flexed slightly as he walked it. It always had. He completed his inspection and walked back to the house to call his neighbor, Dale Purcell, who farmed 300 acres on the far side of the creek. "Water's at 31, Clarence said. "I'd move your equipment to high ground if I were you." "You think the bridge will hold?" Dale asked. "I think the bridge will hold," Clarence said. "I'm less sure about the roads on either end." By nightfall on April 9th, the Whitfield Bridge had become the most important piece of infrastructure in Izard County. County Road 8 was closed. State Route 58 was closed. County Road 22 was closed. The only way to cross Piney Fork Creek between Melbourne and the county line, a corridor of about 14 miles, was the Whitfield Bridge on County Road 14. Emergency dispatch in Melbourne received the first call at 7:43 p.m. A woman on the far side of the creek in labor, 37 weeks. The ambulance crew, Deputy Sheriff Ray Hutchins, and a volunteer fire truck all converged on County Road 14. They stopped at the bridge entrance. Ray Hutchins got out of his cruiser and walked to the edge. He shone his flashlight on the structure. The water was now 3 feet below the deck. The current was pulling hard at the base of the abutments, but the abutments were holding. The bridge itself showed no signs of distress, no cracking, no deflection. The lattice walls were intact. Ray Hutchins had driven across the Whitfield Bridge several hundred times. He knew it was scheduled for demolition in September. He got back in his cruiser and drove across. The ambulance followed. The baby was born at 11:14 p.m. at Baxter Regional Medical Center. Healthy, 7 pounds 4 ounces. Her parents named her April. The flood crested on April 10th and began to recede on April 11th. By April 13th, Piney Fork Creek was back within its banks. The damage assessment began. County Road 8. Approach reconstruction required. Estimated cost $47,000. Estimated timeline 6 to 8 weeks. State Route 58. 3 girder spans to be reseeded. Estimated cost $280,000. Estimated timeline 8 to 12 weeks. County Road 22. Embankment reconstruction and full deck replacement. Estimated cost $195,000. Estimated timeline 10 to 14 weeks. Total road and bridge damage in Izard County from the April 1995 flood, approximately $2.1 million. The Whitfield Bridge, no structural damage. Estimated repair cost, $3,200 for deck plank replacement. Estimated downtime, 0. For 3 weeks, from April 9th until April 30th, when the last alternate crossing was certified, reopened, the Whitfield Bridge was the sole link between the two halves of Izard County across Piney Fork. Farm trucks crossed it. Emergency vehicles crossed it. School buses, feed delivery trucks, propane tankers, combine headers on lowboys. Not one of them caused the bridge to fail. Arthur Finch drove back to Izard County on May 3, 1995. He did not call ahead. He found Clarence Whitfield on the porch, splicing a section of rope. The corn was planted. The weather had cleared. The creek was running peacefully at its normal spring level. Arthur sat down in the same chair he had sat in before. He set his laptop bag on the floor and did not open it. "I owe you an explanation," he said. "You don't owe me anything," Clarence said. "You were doing your job. My analysis was wrong." Clarence looked at him. "Not the load calculation exactly," Arthur said. "The methodology. I modeled your bridge as a series of independent beam elements connected at pin joints. That's the standard approach for timber trusses. But a town lattice truss is not a standard timber truss. The redundancy of the system, the number of load paths, the semi-rigid behavior of the treenail connections, the composite action between the multiple layers of planking, none of that was captured in my model. The SAP 2000 analysis was accurate for what I modeled. What I modeled was not your bridge." Clarence said nothing. "The bridge handled a Category 4 flood event," Arthur continued. "My analysis said it couldn't handle Category 3. That's not a small error. That's a fundamental misunderstanding of how the structure works." He paused. "I need to understand it correctly." Clarence looked at him for a long moment. Then he set the rope splice aside and stood up. "Come with me," he said. "I'll show you how it was built." They spent most of that day in the bridge and on the creek bank. Clarence had kept his grandfather's original construction notes, not formal plans, but a handwritten journal in a school composition book, with sketches and dimensions and annotations in the careful, angular handwriting of a man who had taught himself to read from the Bible and the almanac. He let Arthur photograph every page. He explained the construction sequence, how the lattice panels had been assembled flat on the ground, each plank laid at a specific angle, each intersection marked and bored with a hand brace and bit, each treenail driven and trimmed flush, how the treenails had been made from straight-grained white oak, split rather than sawn so that the grain ran continuously without interruption, how the cord members at top and bottom had been laminated from multiple planks with staggered joints so that no two splices occurred at the same point, how the deck planks had been laid diagonally rather than perpendicular, a seemingly minor detail that increased the torsional stiffness of the floor system significantly. Arthur Finch took 12 pages of notes. He asked questions that became more specific and more technical as the hours passed, and Clarence answered them with patience, translating between the vocabulary of a 19th-century carpenter and the vocabulary of a 20th-century structural engineer with a fluency that suggested he had been waiting for someone to ask these questions for a long time. "Your grandfather's notes," Arthur said, late in the afternoon, sitting on the bank with the composition book open on his knees. He mentioned something called distributed redundancy. He uses that phrase several times. Where did that come from? Clarence thought for a moment. He said Elias Carr told him that a town lattice bridge works the way a healthy man works. If one muscle is injured, the others take up the load. The body compensates. A man with a broken arm can still carry a heavy weight because the other arm and the legs and the back all adjust, but a machine with a broken part stops working completely. Arthur wrote that down. A town lattice truss, he said slowly, is a biological load distribution system. I don't know what that means, Clarence said. It means your grandfather was describing something that structural engineers are still trying to quantify mathematically. Arthur closed his notebook. In 1995, SAP 2000 can model linear elastic behavior in timber frame structures with reasonable accuracy. But the behavior of a highly redundant system under dynamic loading where load redistribution occurs continuously as individual members flex and recover, that's beyond what the software can reliably predict. Not because the software is bad, because the mathematics to describe that behavior accurately hasn't been fully developed yet. Clarence picked up a stone from the bank and turned it in his hand. My grandfather would have said the mathematics will catch up eventually. In the meantime, the bridge keeps standing. Before he left that evening, Arthur Finch sat in his truck and wrote on a yellow legal pad because he needed to think in a way that felt different from typing into a computer. 3 modern bridges had failed in less than 24 hours. The Whitfield Bridge, 34 years old, built without permits, scheduled for demolition, had not only survived but had served as the county's primary emergency corridor for 3 weeks. A baby had been born because an ambulance could cross it. Livestock had survived because feed trucks could cross it. An entire county had kept functioning because one 78-year-old man had built something correctly 34 years ago. He picked up his 2-way radio and called the regional office in Batesville. "This is Finch," he said. "I need to request a suspension of the demolition order for the Whitfield Bridge in Izard County. I'm also going to recommend a full structural reassessment using updated methodology." He paused. "And I want to talk to Dr. Sellers at the University of Arkansas." The formal recommendation to suspend demolition was filed on the 15th of May 1995. It was 17 pages long. It argued that the SAP 2000 analysis had underestimated the bridge's load capacity due to methodological limitations in modeling highly redundant timber lattice structures, and that the bridge's performance during the April 1995 Category 4 flood event constituted field evidence that superseded the computational prediction. It also argued on page 14 that the Whitfield Bridge represented a category of structural knowledge embodied in the builder's craft tradition rather than in engineering textbooks that was disappearing from American practice and deserved systematic documentation before it was lost entirely. The County Board of Supervisors voted 4-1 to accept the recommendation. The demolition order was formally canceled on the 1st of June 1995. The Whitfield Bridge was listed on the Arkansas Historic Preservation Register on September 22, exactly 1 week after the originally scheduled demolition date. Arthur Finch contacted Dr. Margaret Sellers at the University of Arkansas in June 1995. Their initial conversation lasted 2 hours. She had been studying covered bridge engineering for 11 years, had published 3 papers on the subject, and had been waiting for someone from the State Highway Department to call her since 1988. Together, they developed a research proposal to conduct a comprehensive structural assessment of the Whitfield Bridge. Physical load testing with calibrated sensors, 3-dimensional photogrammetric documentation of the lattice geometry, and a detailed analysis of the treenail connection behavior using small-scale test specimens. The proposal was funded by the Federal Highway Administration in November 1995 for $87,000. The research began in January 1996 and continued for 2 years. Clarence Whitfield participated throughout, not as a formal research subject, but as a consultant and guide. He attended every site visit. He answered every question. He showed the research team where the treenails had been driven, which members had been replaced and when, how the deck had been relayed in 1978 after a cattle truck broke through 3 planks. He translated the composition book, his grandfather's notes, into language the engineers could work with. The research team's final report, published in 1998, contained a finding that would be cited in covered bridge engineering literature for years afterward. The load capacity of a town lattice truss bridge under dynamic loading conditions was systematically underestimated by standard finite element analysis methods, by a factor ranging from 1.4 to 2.3, depending on the degree of redundancy and the moisture content of the treenail connections. The report recommended a revised assessment methodology specific to lattice geometry. Arthur Finch was listed as a co-author. It was the first academic publication of his career. He framed the acknowledgments page, which included a note of thanks to Mr. Clarence Whitfield, whose bridge taught the research team more than any textbook, and hung it in his office. Clarence Whitfield died on the 3rd of March 2001. He was 84 years old. He had continued farming until the previous autumn. His grandson, Thomas Whitfield, found the composition book in a cedar chest in the farmhouse, along with a handwritten note tucked inside the front cover. It read, "The engineer came back. He asked the right questions the second time. That's all any of us can do. Ask better questions when the first ones don't give us the right answers. The bridge will be here when neither of us is." Thomas Whitfield gave the composition book to the University of Arkansas Engineering Library, where it was cataloged, digitized, and made available to researchers. The Whitfield Bridge on County Road, 14 inches, Izard County, Arkansas, is 63 years old. It has been repaired 4 times since its construction deck planking replaced in 1978 and again in 2007. One lattice panel replaced in 2014 after an ice storm, the cedar shake roof replaced in its entirety in 2019. The bridge is open to traffic. It carries light vehicles and trucks up to 5 tons. It is listed on the National Register of Historic Places. Every April, the Izard County Historical Society conducts a walking tour of the bridge. Attendance averages 60 to 80 people. They come to walk through it, to put their hands on the lattice walls, to feel the slight flex of the deck planks underfoot. Arthur Finch retired from the Arkansas Department of Transportation in 2010 after 15 years as chief bridge engineer. In his retirement remarks, he described the Whitfield Bridge as the most important structure he had ever worked on. "I went there to tear it down," he said. "I left having learned something about engineering that no software has ever been able to fully replicate. The lesson is simple, and it is old. Redundancy is resilience. Distribute the load. Give the system more paths than it needs, and it will find its way through anything." He paused. Clarence Whitfield knew that in 1961. He learned it from a man who learned it from a Civil War bridge builder who learned it from Ithiel Town in 1820. The knowledge traveled 200 years through human hands before it got to me. He paused again, and when he spoke, his voice was quieter. I almost demolished it. On the interior wall of the bridge, someone has written in black marker on one of the diagonal lattice planks, near the midpoint of the span, "Distributed redundancy, Whitfield 1961. The marker has faded to gray. The plank is solid white oak, dense and hard, carrying its share of the load the way it was designed to carry it, distributed, patient, resilient. The bridge is open. Come across."